Okay, so today's lecture will go to more examples on combinational logic circuits. Basically, in combinational logic circuits, we need to have inputs and a desired outputs. So how can we get the desired output based on the available inputs? So this is an example for creating a code conversion, and we need to build a hardware circuit on it. So basically, we have BCD notation. We need to convert this to XS3. XS3 code. So in the overall XS3 is basically the same as the PCD but add 3, which is plus 3. So here we have, this is equivalent to 0. 0 plus 3 will be 3, then equivalent will be 0, 0, 1, 1. So for example, here is, let's choose the number, this is equivalent to number 8 plus 3, which is 11. This will be equivalent to 11. So XS3 means add 3 to any digits. So put any value, the output will be plus 3. That's what does XS3 mean. So how can we get the outputs based on these inputs? We need to build a digital logic circuits based on it. So in this scenario, we don't have time, so it's not associated with time. Therefore, it's combinational. It's not sequential because there is no time dependence. And the BCD, I'm sorry. So as we know in the PCD, we have 4 inputs to get 4 outputs. So we need to build a truth table. If here's, let's assume the truth table is given. So how can we achieve this? Most likely we have 4 inputs. And these 4 inputs in the Carnot map, we need to have 2 power 4, which is 16 Carnot maps. 16 possibilities of Carnot maps. But here, we realize that in this truth table, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 6 left, 6 more. But we don't have them. So how can we complete this truth table? You can complete this by making 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay? So in these possibilities, since we don't have any information about the rest, then we mark them as don't cares. We will mark them as don't care. Sometimes in textbook we call them D. So the missing, when we build the truth table, any missing elements on the truth table, we will mark it as don't care. So in general, like if we need to make it as min terms, here is M0, M1, M2, M3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we will realize from number 10 up to 15, they are all don't cares for all of these 4 outputs. Okay? And since we have 4 inputs, we will have 4 variable Carnot map. So we need to build 4 Carnot maps to solve this question. We need how we make every output, or we need to have 4 variable Carnot maps for each output. Let me write it here. 4 variable Carnot map for each outputs. How many outputs do we have? 4. Therefore, we need to build 4 variables Carnot maps, which will take some time, which is like this. Here, I'm going to just make a modification because this will be, here is CD, here is AB, here is CD, here is AB, CD, AB, CD, AB, and I can make the guidelines, which is here is A, here is B, here is C. Oh, I think I messed it up. Let me do it again. Here is C, here is D, here is A, here is B. A, B, C, D. A, B, C, D. A, B, here is B, here is C, and here is D. Okay? Then write the midterms list, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here again, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? I'm sorry. Now, look at the variable W. What are the midterms with variable W? Then look at X, then Y, Z. For variable W, the midterms are 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. And the don't cares associated with it are 10, 11, 12, 13, 14, 15. Those are the don't cares. How about variable X, which will be between 1, 2, 3, 4. 1, 2, 3, 4. Then number 9. How about variable Y? 0, 1, 2, 3, 4. 3, 4. 7, 8. How about variable Z? 0, 2, 4, 6, 8. And again, don't forget the don't cares. Okay? Then let's look at the ones. Again, here let's put the variable W here. This for variable X, this for variable Y, this for variable Z. Okay. In W, let's look at the ones. W, the ones are at 5, 6, 7, 8, 9. Come on. 5, 6, 7, 8, 9. How about the don't cares? The don't cares are between 10 to 15. Don't cares from number 10, 11, 12, 13, 14, 15. Okay? Sorry. Let's look at for variable X. Let's put the ones, then we will make simplification. 1, 2, 3, 4, 9. 1, 2, 3, 4, 9. Then from 10 to 15, don't cares. 10, 11, 12, 13, 14, 15. How about variable Y? Variable Y, 0, 3, 4, 7, 8. 0, 3, 4, 7, 8. Then the others take care from 10, 11, 12, 13, 14, 15. Then the last one for variable z, 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. Then the don't cares are at 10, 11, 12, 13, 14, and 15. Okay, understood? Now, let's make the kernel maps, or make the loops. Our target is to make the bigger possibility, the bigger possible loops. So, let's start with variable w. W, we can make this, right? This is the biggest possible. Now, we have, let's see, W, 5, 6, 7, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. Okay. Now, we have 3 ones in the lifts. What should we do? How can we cover this? We can cover this as 4 loops. We can take a group of 4 like this. Let me change a different color. And we can cover as a group of 4 like this. Okay? Sorry. So in W, so the bigger loop will be at variable A. So it will be A. Plus, when there is a loop of 4, this means 2 variables. So the blue loop between D and B. So plus BD. Then the purple loop will be between C and B, so BC. Okay, clear? This is for variable W. How about variable X? Variable X, our target is to make it the bigger possible number of loops. Number of loops. So we have these 2 with these 2. So we can make it 4, right? Then we have these 2 with these 2, right? Now there is this one left. What shall we do with this? Can we make it with 4? No. Can we make it with 2? Yes. So we can make it with 2. Okay? So the overall, when there is a loop of 4, 2 variables, a loop of 2, 3 variables. So let's look at the pink loop. It will be between D and B bar. So B bar, D. This is in pink. How about in purple? Between C and B bar. So plus B bar C. How about the orange? The one in orange, 3 variables, which will be B, C bar, D bar. B, C bar, D bar. Okay? Does this make sense? Sorry. Let's go to variable Y. Variable Y, we have, let's see how many possibilities we can achieve. Can we make it 8? No. Make it 4? Yes, we can. So we have this 4, and we have this 4. Then that's it. So for variable Y, we can say that the orange one will be 4 variables, which means includes 4 blocks, which include 2 variables. These variables are C bar, D bar. C bar, D bar, plus the this one in the orange. How about in the pink? Will be CD. Okay.
The last one. The last one, can we group it as 4? Yes. But let's try to think by the biggest number of loop possible. So the biggest number, can we make it a group of 8s? Yes, we can. Or like 16 we cannot, but 8 we can. So we can make this 8. So 8 means they are including one variable. And this variable is d bar. Okay? So in our design, the first part, we have the inputs, put the outputs. Then we determine the min-term list. So if you need to draw these circuits in canonical form, not the simple form, we can just draw it like using the min-terms. But our targets in our design to make it as minimum as possible. Why we needed this? Because if we need to build multiple boards, then we can save the costs. So we need to minimize it. So we minimized it using the canonical form until reaching these functions. So these functions, of course, are easier to implement or cheaper to implement than the original one or the first assumption. So overall, the functions, I'm going to write them here. W is A plus BD plus BC. Variable X is B D bar plus B bar C plus B C bar D bar. Variable Y is C bar D bar plus CD, and variable Z is D bar. I'm sorry. Okay. Now, how can we implement this into electrical logic circuits? I prefer, when drawing the circuits, to make the inputs, this side here is A, here is A bar. Here is B, here is B bar. Here is C, then C bar. Then the last one, D, here is D bar. So we have 4 outputs. We have the outputs W, X, Y, Z. So let's start with Z first. Z equal to D bar. So here is D bar, then here is the output C, Z. Y equal to C bar, D bar plus CD. C bar, D bar, which is AND, then plus, which is OR, CD. CD, which will be AND. So let's do C bar, D bar first. Here is C bar. Let me make it in a different color. C bar, D bar, they will go with AND gates. Then we have CD, they will go with another AND. Then both will go with OR gates to make variable Y. How about W? W, it will be, the variable X first, B D bar plus B bar C plus B C bar D bar. So we need to make the gates, which is 3 AND gates, then there will be OR. So 3 AND gates. Then they will be connected with OR to create the variable X. So the first AND gate will be with B D bar. So here is B, then here is D bar. The second one with B bar C. Here is B bar, then here is C. The third one with B, C bar, D bar. So let's go to B first. then C bar, D bar. Here is C bar, then here is D bar. Then we are done with variable X. So the last one is the variable W. So the variable W, there is A, BD plus BC. So we have A first, then BD, here is B, here is D, then with AND gates, then there is BC. So here is B, and here is, where is C? Here is C. With AND gates. Then there will be with OR to create the value W. Okay. Now again, in hardware, maybe I don't have AND and OR. Maybe I have NAND implementation or NOR. And you know, of course, you know how to convert this to NAND implementation or NOR implementation. So it's depending on the question. If the question didn't mention anything, then that's enough. If the question say convert this to NAND implementation, then keep this in mind. If you need to convert this to NAND implementation, put bubble here, bubble here, bubble here, bubble here. Here is bubbles. Then keep in mind to put an inverter here. Okay? Then that's it. So after building this circuit, I'm sorry, you can go to the lab and say, this is my circuits. Then you can build your hardware circuits. So that's your design. That's your program, it's called hardware program, that you can convert any inputs to get to achieve XS3 code. So you build your own software or your own program based on digital logic circuits. Then this design, you can convert anything. So that's how we do, not only for the like XS3, this is one example because we have multiple inputs, multiple outputs. You can apply it for any practical problem. Then that's how we do our designs. Well, any question about this? Okay, let's go to another one. Drive truth table, and I'm going to call it sum of products of the circuit because it's sum of product, not product of sum on this circuit. Look at the circuits. So now I'm doing like reverse engineering. Assume you work in a company, you work in a lab, then they give you this circuit. So they told you, we need to identify this circuits. What's the purpose of this circuit? Or how can you detect this? So now we are doing, again, reverse engineering to see how is, I already have a system, I need to see what's the function or what's the origin of this circuit. Then maybe later, if you need to modify on it, you can modify. So how can we do this? Look at the variables. Look at them. This inputs, this is the output F. So first parts, like let's assume that these are not exists. So you need to determine what's the function first, then convert this to canonical form and do the analysis. So let's assume this. So we have, this is the variable X, here is Y, here is Y bar. Then here is the variable Z. Here is the variable X bar. Here is the variable Y, then here is the variable Z bar. Therefore, we get X plus Y bar because there is OR. Here is X plus Y bar times Z because there is AND. Then here is X bar, Y, Z bar. Then we can get the function, which is X plus Y bar, Z plus X bar, Y, Z bar. Okay? Now, we need to do the truth table. How can we achieve the truth table? If we need to build the truth table based on, let's do X, Y, Z, then, for example, X bar, then Z bar, Y bar, and you can do it like this and say like X plus Y bar. Then make the variable like X plus Y bar times Z. then you can make another variable x bar, y, z bar, then make the function, which is their addition. You can build it like this, but this will take so long, and the chance of making mistakes will be higher. So how can we deal with this in an easy way? We already have the function f equals to x plus y bar times z plus x bar y z bar. Yes, that's the function. Now, can we convert this to canonical form? Yes. So one of the good points, we can do the canonical form to find the minterms. Then when we build a truth table, the minterms are the location of ones. And that's it. So we don't need to make that large truth table while we can do it by using the minterms. How? Let's try to simplify it more. So it will be x, z, plus y bar z, plus x bar, y, z bar. Now, not all of these terms are based on 3 variables. So each term includes, this term includes 3 variables, that's fine. But this includes 2, this includes 2. What we need to do? Apply the same techniques that we used to do when we did the minterms. So what's the missing variable in the first one is y. So it will be x times y plus y bar z, plus the other term here is missing is x plus x bar times y bar z, then here x bar y z bar. Okay, do you agree with me? Okay. Now it will be x y z plus x y bar z plus x y bar z plus x bar y bar z plus x bar y z bar. Is there any common terms? Yes, we have this one and this one. So we can eliminate the common and just write one. xyz plus xy bar z plus x bar y bar z plus x bar y z bar. Now, I can say it's like 1, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0. So this is equivalent to M2. Here is M1. Here is M5. And here is M7, right? Then in other words, it can be as sum of minterms of 1, 2, 5, 7. If you need the max terms, in case if you need them, it will be the opposite, like the numbers from 0 to 7. So 0 is not clearly here, 1 is here, 2 is here, 3 is not here, 4 is not, 5, 6, 6 is not here, then 7. Okay. Okay, what's the benefits of getting the min terms or the max terms? When you do the truth table, okay, let's do the truth table. Here is x, here is y, here is z, and here is the function f. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So basically this stands for 0, 1, 2, 3, 4, 5, 6, 7. According to this function, the minterms are 1, 2, 5, 7. So there is 1 at 1, 1 at 2, 1 at 5, 1 at 7. Then the remaining are zeros. Then that's it. So this is the advantage of using the canonical form. Then I don't need to use the old way of making the truth table. Okay? In case if we need to find the mathematical expression or the algebraic expression of the minterms, so here is 0, this is equivalent to 0, 0, 0, 3 is equivalent to 0, 1, 1, 4 is equivalent to 1, 0, 1, 1, 0, 0, 6 is 1, 1, 0. Then we can write, remember in max terms, the 0 means no bar, the 1 means bar. So here it will be x plus y plus z, because in max terms they are the opposites.
then here plus x plus y bar plus z bar, then here times what's called here, this is x bar plus y plus z, then times x bar plus y bar plus z, in case if you need to find the function in max. Okay, any question? So simplifying this is much easier. So here there is no new thing. We already know all of these techniques, but now we are trying to deal with some complicated problems or some some design problems. Okay, this is another example. We need to do the combination of these numbers. So we have 4 bits, and 3, and 2, and 1, and 0 produces 1 when n equal 1, 2, 3, 4, 5, 11, 13, which is for the prime numbers, and 0 otherwise. We need to determine or to find the NAND gates or make the NAND gates implementation for this design. So look at this one. Here it will give you if the input is prime number. So it's like, it looks like you are building a device like a prime number detector. When there is a prime number inputs, it will give you a lights, or the light will be on. If there is no prime number, the light will be off, just like a detector. So how we realize that the prime numbers are 1, 2, 4, 5, 6, 11, 13. Then here we have the combination N3, N2, N1, N0. Actually here, we don't need to build a truth table. It's already been given the midterms based on the prime numbers inputs. So we can say that the midterms are the given 1, 2, 3, 4, 5, 11, 13. It's already been given. So the first step of building the truth table, determining the inputs, are the first step is done. So what should we do next is to build the function or to make the function. How can we create the function? Build the kernel map, because we need to make it the design in the simplest way. So here is the combination will be like, we used to do it like N3, N2, N3, N0, N1, Y plus X. Okay, I'm sorry, let's do it again. Let's do the N0, N1 here, then here, N2, N3. Okay. 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Here is the location of N1. Here is the location of N0. This is the location of N2. This is the location of N3. Now let me write the midterms location. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, here's 8, 9, 10, 11, 12, 13, 14, 15. Now let's put the location of ones. The location of ones are at 1, 2, 3, 4, 5, 11, 13. I don't know why 7 is not here. Is 7 a prime number or not? I'm not sure. Yes, but why it's not written here? That's weird. Okay, let's assume the problem is like this. Now, seven is a prime number, and this problem is not written. Okay, anyway.
4 is not a prime number.
Which one? 4 is not a prime, right? So I think there's, let me make 7 instead of 4. Okay, so here's 7. I'm gonna erase 4 and put 1 at 7. Okay. Now we need to group this to build the circuit. So let's group. We can group these four. Okay. Then what else? We can group these two. We cannot make it in four. Then we can group these two. And the last one, we can group it this way, right? So let's do the function. So the function f will be, let's look at the bigger loop in pink, which should include two variables. These two variables are n0 and 2 bar. So n2 bar n0. Is this right? So here is n0 and 2 bar, right. Then let's look at the blue color. It should include 3. These 3 are basically n3. n2 is not an option. n1 bar, n0. Then let's look at the one in green color, which will be n3 bar. N2 is not an option. N1, N0. Then the last one, which is in orange, it's going to be N3 bar, N2 bar, then N1. Yes. Okay. So I assume everyone knows how to do kernel maps, so should be all right. So after building the function, we can create the circuit, build up the circuit. So here is N3, N2, N1, N0. This is the design. Here is the prime, the bar. Oh, sorry. Okay. Now we have 1, 2, 3, 4. 4 AND gates. Then they will be connected with OR because sum of products. To get the function f. Okay, so the first one will be with N2 bar N0. N2 bar N0. The second one will be with N3. Here is N3. N1 bar. Here is N1 bar. N0. Here is N0. The third one will be with N3 bar. Here is N3 bar. N1, N0. Here is N1. Here is N0. The third one, or the last one, the fourth one, will be with N3 bar. Here is N3 bar. N2 bar. Here is N2 bar. N1. Here is N1. Then this is the function. This is not the end. Question says NAND gates. Convert this to NAND gates. How can we convert this to NAND gates? Basically, here is bubble, bubble here, NAND gates, bubble, 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 bubbles. Now they are all in NAND gates, and that's enough. You don't need to redraw this to be like this. You can redraw it and do it like this way, or that's enough. Because because this one, come on, what did I do? Yes, okay. This one and this one are the same. These two are the same. Then that's enough just to make the bubbles. Any question? So you see, these kind of designs are just like a practical problems, a real life practical problems, so we can know how to design our own circuits. This is another example from the textbook, problem 331. So alarm controller that's designed to sense 4 input signals. We have line A from a secret control switch, line B from a pressure control to steal safe lock closets, line C from a battery power clock, line D, which is connected to the switch that's locked the closed door. So the following condition produce logic A. So the logic A, the voltage and the corresponding input. So again, sensor A, here is the control switch is closed, will give us the logic A, or this condition. So the safe is in its normal position in the closets. The clock is between 0900 to 1600 hours. The closet's door is closed. So write a logic expression for the burglar alarm that produce a logic 1 rings. So rings a bell when safe is moved and the control switch is closed. Safe is moved, control switch is closed. Or when the closet is open after banking hours. So the first condition, safe is moved and the control switch is closed. The second condition, or, which means there is a plus, when the closet is open after bank hours. Then or, there is plus. Third condition, when the closet is open with the control switch is open. So we have 3 conditions that will turn on the switch. So let's look at condition number 1. Condition number 1, or our target, is to make the bell ringing. So F is the bell ringing. So basically it's just detection if there is any burglar. So number 1, if safe mode is on. Safe mode is on means B. B is related to safe mode, and it is on. The normal position is not in its position, so it will be B bar. So the normal position is off, it will be on B bar. Then, what else? And means dots. Control switch is closed. Control switch, where is it? Is the control switch is A, and the normal state is closed, then times A. Okay? The second condition, when the closet is open. Look at the closet sensor is D. The closet door is closed, therefore open. It's the opposite, and it will be D bar. After that, after banking hours, look at the clock is between 0900 to 16 hours, which is this the hours of the bank. Then if it's after hours, we'll make C bar. So it will be D bar, C bar, because it's after hours. Then number 3, when the closet is open, look at the closet sensor. The closet sensor is D. Open means D bar, because the reel is closed. And the control switch is open. Control switch is closed, which is part A. If it is open, means A bar. Okay? Did you get it? Therefore, we can say F equals to, we can make it an alphabet order, A, B bar, plus C bar, D bar, plus A bar, D bar. Now we converted the verbals problem into digital logic problem. So we can create a design that we can connect it to the bank by using these conditions. So how can we create this? Actually, this has already been designed into the simplest way. If you want to verify this, you can verify this, write this in canonical form, do kernel maps, and do it. So you will realize that this is the simplest way, so we don't need to do any simplification. So we can say that here is A, this is A bar, B, here is B bar, C, here is C bar, D, here is D bar. Then we have 3 AND gates. Then they will be connected with OR. This is the function f. So the first one will be with A, B bar. A, B bar. Second one will be with C bar, D bar. C bar, D bar. Third one will be with A bar, D bar. Here is A bar, here is D bar. And since we need to convert this or to more practical circuit, which is converted to an AND implementation, so put bubble here, bubble here, bubble here, bubble here, bubble here, and bubble here. Then this is a NAND implementation. After that, you can build your own circuits into a board, put AND gates, connect them like in this way, so you can go to the bank and tell them, here is the design that I built, so it can detect any burglar activities there. So you can connect it to your system, then you can sell your product to the bank. So you can build a security system. And you can do it in hardware, which is using the digital logic circuits. So you see, it's so simple. Okay? This is one of the most practical, or one of the common practical problems. There's problem 325. Long hallway has 3 doors, one at each end and one on the middle. One at each end, so there is one door at each end and one in the middle, 3 doors. So which is switch A, B, C. So a switch is located at each door and operates lights along with the hallway. Label switches A, B, C as I do here. Assume the flipping any of the switches will turn on the light on if it is currently off, or off if it's currently on. Write a code about this. Basically, when you enter this, the first door, the light will be on. Then when you go here, it will flip, it will be off. Then when you go here, it will be on, right? Or in other words, if it was the opposites, if the light originally was on, then you enter here, it will be off, enter here, it will be on, enter here, it will be off. So now how can we create this function? We will realize that we can count if the sensor being detected. Sometimes someone can enter this door without entering this door, and someone can enter this door. What will happen? This will make switch twice, so it will make F0. If 3 people entering, this will make it 1, 2, 3, which is on, off, on, then it will make it on. So as a result, we will realize that the odd number of detection, odd number will make it 1. Even number will make it 0, which means the odd numbers of entering the doors, because to make it, for example, on, off, on,
we'll make it on. How about like off, on, or I'm sorry, on, off, or like on, then we have 1, we'll make it off. Then this is 0, there is no switching. So any switching action will make it off. So as a result, if there is any odd number of switching actions, it will make it 1. If even numbers, it will make it 0. Or in other words, we can say odd number of ones will make it 1. Odd or even number of zeros will make it, of ones will make it 0. So as a result, we can build our own truth table like this. Here is, I'm going to draw it. Okay, I'm going to draw it here. Here's A, B, C. Then here's the function for the lights. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So here's, we can say this is 0, 1, 2, 3, 4, 5, 6, 7. So here is, there is no number of 0, then will be 0. Here is odd will be 1. Here is odd will be 1. Here is even will be 0. Odd 1, even 0, even 0, odd 1. Just make it at the odd. After that, we can build our kernel maps, 3 variables kernel maps. So the kernel maps will look like this. So here is variable C, here is A, B, 0, 1, here is C, 0, 0, 0, 1, 1, 1, 1, 0. Here is A, here is B, then this is 0, 1, 2, 3, 4, 5, 6, 7. Then look at the location of ones, which will be at 1, at 3, then, I'm sorry, at 2. At 1, at 2, at 4, then at 7, like this. Now, can we group this? We cannot group it. Therefore, there will be 3, or there will be 4 separated functions. So f will be the first one, which is for M1. Then it's going to be as A bar, B bar, C, because M1 will be 0, 0, 1, plus here is M2, which is going to be 0, 1, 0. Then it's going to be A bar, B, C bar, plus M4, which is going to be 100, 1, 0, 0. So 1, 0, 0, which is going to be as A, B bar, C bar, then plus the last one, which is M7, 1, 1, 1, then ABC. Okay? Now, how can we build the circuits? I'm going to do it here. Here is A, B, C. This is A bar. Here is B, B bar. Here is C, C bar. So we have 4 AND gates. 1, 2, 3, 4. Then we have OR gates here to get the function F. So the first one will be with A bar, B bar, C. A bar, B bar, C. Second one, A bar, B, C bar. Third one will be with A, B bar, C bar. A, B bar, C bar, and the last one will be ABC. Here is A, here is B, and here is C. So to get the function F, to make it more practical, we put, to make it NAND implementation, so we can implement this in hardware, so we can do this. So we can make apply this and build the circuits into a practical problem. Okay, any question? So here, the binary adders, or the next slides, we already discussed this in the previous lecture. So multiplexers, decoders, have adders, encoders, active low, active high. It's already been discussed. Then the next topic will be in chapter 4, which is sequential logic circuits. Okay? Sequential logic circuits are associated with there should be at memory or at time, something dependent with time. So these time dependence, which means this time matters with this. Like, for example, when you are building a circuit for traffic lights, so the times matters with it. So we need to worry about what to do, and how the system can store the memory. So if we need, like, the computer to build a memory drive, how can we deal with this? How can it store? That will be our targets in next chapter. So we will talk about the sequential, which is, there are two types, like synchronous sequential or asynchronous. That will be next lecture. And there will be something associated with the clock sequential logic circuit to make it synchronous. So this clock, similar associated with the time, like tick tock, tick tock. This will make it changing with time. And there is another type, like counter. So it's not like tick tock. You will press the button depending on what you see. So it can be as timer or as counter. Sure. The difference between timer and counter, the timer is depending on the clock, like tick tock, then time will be counted. While counter, you will count. So 1, 2, 3, and press in the counter. So you will determine what's the clock. So all of them will be depending on, like, if it is synchronous or asynchronous. Synchronous will be based on clock. Asynchronous, you will press. Then the other thing, which is based on, there's something called SR latch and flip-flops. SR latch is something, or a storage element, or a storage device it can store the signal and it can be erased easy. Like flip-flop, I'm not sure, maybe I confused between them. And the flip-flop will store and keep it, store and hold. So this thing, we will discuss this next lectures. We will see how we'll try to build something called timing diagram to see how the situation will be. So that will be our topic in the next lecture, and how we build a real life storage elements based on the hardware components that we have. So we will go to all of this in the following classes. So there are different ways on doing it. Then I think that's it for today's lecture. Thank you.